let's do one more example, and don't worry, we're not going to draw the actual Turing machine. We're going to focus on high-level pseudocode, okay? And then we'll move on to conceptual issues relating to what we can and cannot compute. So what's this example we're going to do? Let's do multiplication. So I'm going to define the language, L multiplication. Okay, so this is the multiplication problem, and it's a language because the computing problem is a language. Okay? So it's the set of strings, some number of zeros, 0 to the n, punctuation, 1 to the m, punctuation, 0 to the m, to the n, times n. Okay? So if you're going to solve this problem, it means that you take a string and say yes or no, it's in this set. Okay, and to say yes that it's in this set, you have to verify that it's zeros, followed by ones, followed by zeros, and the number of zeros here is the product of the number of left zeros and the number of ones. So you have to verify that you know the number of zeros here is a product, and that's why we say it's equivalent to multiplication. You're performing multiplication, and this plays along with the theme of almost any problem that we would like to solve. In fact, any problem we would like to solve can be posed as a decision problem. Okay, now. How do we solve this? Let's start with an example. Okay, so here's my Turing machine, looking at its tape. Okay, so you have your beacon symbol. Okay, and the Turing machine starts, here. Okay, and then, let's say we have 0, 0, punctuation 1, 1, 1, punctuation 0, 0, 0, 0, 0, 0, and then for good measure, the space symbol. So here are the slots of my tape. Okay. And now we need to build a Turing machine algorithm, high-level pseudocode that's going to solve this problem. For example, be able to say, yes, this string belongs to my set. Okay. And in building Turing machine algorithms, the challenge is that, you have to sort of put yourself into the mindset of the DFA that's sitting here. So currently the DFA is sitting here, and all it can do is look down and see this star. So yes, there's tape on one side, tape on the other side, and there's an input on one of the sides. Okay, and I'd like to look over there and see, oh yeah, I see zeros, ones, zeros. Oh yeah, that number of zeros, there's the product, and I'm done. But you cannot do that. Okay? The capabilities of this machine that you have to put yourself in the mindset of is I can only look down and see the star. And now I'm looking at the star and I need to decide what to do. So I ask myself, what state am I in? Oh, I'm in the state that says if you see star, move. Okay, now I'm going to see 0. If you see 0, move. Okay, now I'm going to see 0. Okay, if you see 0, move. Okay, and now I see pound. Oh, you see pound, change state and move. Okay, so these are the kinds of things that the Turing machine can do. Okay, and we need to build an algorithm to solve multiplication that can be solved, that can be implemented using that baby capability of just being able to look down and move. Okay, so, even though I'm here and I'd like to know what's over there, I'd like to look and see, oh, there are 6 zeros. I cannot do that. The only way I can get over here is to actually move here and then see that there's a 0 there. Now, one way to solve this problem is to realize that multiplication is just repeated addition. Okay, multiplication is just repeated addition. And then you might say to me, how did you know to do that? That's the creativity in solving a problem. It has nothing to do with Turing machines. And you've experienced this in your programming classes. You're given a problem and you need to use some creativity to come up with an algorithm to solve the problem. So we had to figure it out. And I'm just proposing one idea. Okay. And so, okay, what does that mean? That means that, 2 times 3 is really 3 plus 3. 3 added to itself 2 times. So one way to verify that the number of zeros here is 2 times 3 is to say, okay, for this 0, can I match, this batch of ones with an equal batch of zeros? Then for the second 0, can I match this batch of ones with an equal batch of zeros? And if I do, if I can manage to match both batches, it's true. This is the product. Okay, and if I cannot, it's not the product. Okay, so that's the idea. Okay, now, how would we actually implement that? So that's where I'm going to build the pseudocode, and we'll work through the pseudocode with this example and see how it actually works. It involves the Turing machine zigzagging just like we did for W for repetition, and that's generic for Turing machines. And that's due to the ability that, I can only look down. And so if I want to know what's going on over here, I have to move. So Turing machine typically zigzags all over the place. Okay, so let's build the algorithm. Step 1 is very easy. Check the input format. Check input format, and the format we require is that it's some number of zeros, pound, some number of ones, 0 to the I, 1 to the j, pound, some number of zeros, let's say 0 to the k. Now, in this step, we're not verifying that k is the product. We're just saying that the format of the string is zeros followed by ones followed by zeros with punctuations. In fact, as an exercise, show that a DFA can solve this step. So you can implement this step with a DFA. You don't need the full-fledged capability of a Turing machine that can move back and forth, and write and read and so on and so forth. You just, you start at star and you move just like a DFA moves through the input and says, oh, I'm seeing zeros, happy, 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 come to pound, good. I'm seeing ones, happy, 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 come to pound, good. I'm seeing zeros, happy, 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 come to blank, good. Input format matches. Okay, so DFA can solve that problem. Okay, and then, come back to base. So go back to star. So move left until you come to star. Okay, so the input format has been checked. Now we're ready to implement this idea that multiplication is repeated addition to verify that here lies the product of 3 times 2. So first step, move right and come to the first unmarked 0 and mark it. Move right and come to first unmarked 0 and mark it. That just means, remind yourself or tell yourself that you're processing that 0. So we move right. Okay, so we move right to this 0 and mark it. Okay, good. Okay. What if, when you're moving right, you find no unmarked zeros and come to pound? If come to pound, well, we'll have to do something. So we'll have to go to step something, and we'll fill it out after we flesh out the algorithm. I'll tell you what to do if you come to pound and there are no unmarked zeros. Actually, we'll have to go to step 6 or something like that. Okay, so now that we've marked this and we're processing this 0, we need to verify that this batch of ones has a matching batch of zeros. Okay, so step 4, move right to first unmarked 1 and mark it. Okay, and you can think, if I'm moving right and I go past this pound and I find no unmarked ones, okay, and I come to a pound, it means that there were no ones to begin with. Okay, in which case, you'd have to do something. If you come to this second pound, okay, so so in this step, if you moved right and you came and there are no unmarked ones, if no unmarked ones, okay, i.e. come to pound, okay, basically what it means is that, you've processed all the unmarked ones. You come to this second pound, you've processed all the unmarked ones. We'll have to figure out what to do then. Okay, so question mark. Okay, but move right to the first unmarked one, mark it. So we'll move right to the first unmarked one, mark it. And now the idea is that for every one of these ones, I need to match it with a 0. So, move right to first unmarked 0, to first unmarked 0 and mark it. Move right to first unmarked 0, move right to first unmarked 0, and mark it. Okay. Now at this point you've matched this one with this one. Okay. Now there is a situation that could arise, which is when you're moving right to find a first unmarked 0, you come to blank. If come to blank, so you didn't find an unmarked 0, well then there are not enough bits in here, so you can immediately reject. Okay. And once you mark this, here's what you do. Move left to first marked 1. So move left to the first marked 1. Okay? And you'll see why we do that. Because now we've matched this one to this 0, so we move left to that 1, and we can actually go back to step 4. So think of this as a loop. So what does step 4 say? Move right to first unmarked 1. So move right to first unmarked 1. Okay, mark it. Move to the first unmarked 0. Okay, mark it. Move left to the first marked 1. Mark it. And then move right to the first so move left to the first marked 1. Okay, then come back to step 4. Move right to the first unmarked 1. Mark it. Okay, then move right to the first unmarked 0. Okay, mark it. Okay. And then move left to the first marked 1, okay? And now we come here, move right to the first unmarked one. We don't find an unmarked one, we come to pound. Okay, so what does that mean? What that means is that I've matched all these ones to an equal number of zeros. Okay, and that means that I'm done processing this zero. So what I should do is I should move left, unmarking these ones, and go back to stop. Go back to 2. So move left. Okay. Move left, unmarking the ones until you come to pound. So if you come to pound, if no unmarked ones, move left, unmarking ones. Okay. And then go to step 2. Okay, so what is step 2? Step 2 is go back to start. So move left. So I'm going to move left, unmarking the ones. So I unmark, unmark, unmark. Okay, so I move left, unmarking the ones, and then go back to start. And then I'm back at step 2. So I go back to step 2, which takes me back to start. And look at the situation. I've processed this 0 and checked off an equal number of zeros to the number of ones. Okay. And now I just repeat. So I've gone back to 2. I move right to the first unmarked 0. Okay, so move right to the first unmarked 0. I mark it. Okay. Then I move right to the first unmarked 1. I mark it. Okay. Then I move right to the first unmarked 0. I mark it. Move left to the first marked 1. And then move right to the first unmarked 1 and mark it. Okay, then move right to the first unmarked 0, mark it. Okay, then move left to the first marked 1. So I come to the first marked 1. Then I move right to the first unmarked 1, mark it. Move right to the first unmarked 0, mark it. Okay, and then move left to the first marked 1. Okay, and now move right to the first unmarked 1. I have none, so I come to pound. Okay, and now I've come to pound. So move left, unmarking the ones. Okay, and then go to step 2, which brings me back to start. And now look at what the situation is. Fantastic. I've processed 2 zeros, checked off 2 batches of zeros, and I'm in step 2. So I move right to the first unmarked 0, but there are no unmarked zeros. I come to pound. So go to step 6, which is what I said before. So step 6. All that remains is to keep moving right, okay, looking for an unmarked 0. If you come to blank, that means you have verified that it's the product. If you come to an unmarked 0, it means that this number of zeros is too large. So move right, until, unmarked 0, in which case you say no, or you come to blank, in which case you say yes. That's the algorithm. Boom! Okay, so it'll move right. You move right, come to blank, and in this case you would say yes. Boom! Okay. Now, I'm going to show you a twist. Okay. A twist. What about if we, instead of solving this decision problem, we wanted to actually do multiplications? So here's what we would do, or here's what we might imagine. I don't know, I just have zeros, okay, and I have ones, and I don't have these zeros. I don't have these zeros. So the tape looks like this. This is my input. Okay? And now, instead of, verifying multiplication, what I would like you to do is actually do the multiplication. And this is an interesting possibility that is available with the Turing machine, which was not available with the DFA. The DFA just processes an input. The Turing machine has the ability to, read and write to memory. Okay? So, as it's reading and writing to the slots, you can imagine that I could write to these slots, and what I would like the situation to be after I'm done, okay, after my Turing machine stops, is what I would like is that, there are exactly a number of zeros here which is equal to this product. Okay, so I would like this to be the start of the string, and then I would like the string to look at the end as follows: star, 0, 0, punctuation, 1, 1, 1, okay, punctuation, 0, 0, 0, 0, 0, 0, and a blank. Okay, so I would like the state of the tape to change from this to this, okay? And in which case I would say that I've actually done the multiplication. And you can think of what was written to the tape as the output. So I have an input and an output. And now we are looking more like the computers we're used to. So just to show you that the Turing machine can even do this, okay? And this is called a transducer Turing machine. A transducer is something that changes. So it takes the input and changes the format of the tape, changes the tape to produce an output. So then when the Turing machine is done, you could just look here and see, the product of 2 times 3 is 6 by just counting these zeros. Okay, so that's a transducer. Well, it turns out that this same pseudocode basically, implements that. The only thing I need to change is move right to first unmarked 0. I change that to move right to first blank. And instead of marking it, I write a 0. So I don't need to have this additional step. And then move left to first marked 1. Okay, so let me show you how that works. So I move right and I mark this guy. Then I move right to this 1, I mark it, and I move right to a blank, I write 0. Okay, then I move left to the mark, I move right to mark this, and move right to a blank, write 0. Then I move left to the marked 1, move right to the unmarked 1, mark it, and then I write 0. Okay, and then I move left to the marked 1, come to pound, I go back, erasing, erase, erase, come back here. Okay, then move right to the 0, mark it, then move right to the 1, mark it. Okay, and then move right to the blank, write 0 instead of marking. I write 0. Then I move left to the mark, move right to the 1, move right to the blank, write 0. Move left to the mark, move right to the 1, mark it, move right to a blank, write 0. Move left to the mark, move right to the pound. Okay, and now, I have no more unmarked 1, so I move left, unmarking, unmark, unmark, come back to star, move right to zeros. I see there are no more unmarked zeros. I come to pound. Now I'm done. I don't need to even go to step 6. Okay. So get rid of this, go to step 6. Okay. And then check the input format doesn't need, well, we can just put a pound. Okay. And this guy here implements the transducer Turing machine that takes this input, the original input, to the changed input, which has an output. That's called the transducer Turing machine. That's more like a program that takes an input and an output. Okay, so we're getting closer to the computers that we know and love. Okay, so this is just to show you that the same basic pseudocode can be easily converted into a transducer. Okay, that's just emphasizing, further reinforcing the fact that the decision problems are basically all we need to study. We can basically do everything if we can study the decision-making capabilities of this Turing machine, and so we'll continue to focus on decision problems. Okay, and let's erase. And now we're going to come back and talk a little bit more about the conceptual side. We're going to introduce some conceptual issues and move towards what can we and what can we not compute.